Okay, so now that we know how to go from a molecular formula to a proposed structure to a 3D shape, we're going to see how shape affects the physical properties of the molecule. This really requires you to be able to picture the molecules in 3D. It really depends on that overall shape, so you definitely need to practice that. Okay, so first up, polarity and dipole moments. Okay, the overall polarity of an entire molecule, or molecular polarity, quite obviously, affects its chemical and physical properties. We'll see that today. It actually affects their boiling points, their melting points, and solubility, and other things. And so before we get to the molecular polarity, though, this is again the polarity of an entire molecule, we should first reiterate about bond dipoles and dipole moments. Okay, so recall that we can have polar covalent bonds between atoms of a different electronegativity. So here is a carbon-oxygen bond, and if you look at the different polarities between those atoms, which one is more polar? Look on the periodic table. The oxygen is more polar, so it pulls electron density more to its side, right? The polar covalent bonds, right? The electrons are being shared, but they're being shared a little bit more towards the oxygen because it's pulling, it is more electronegative, and so it has more ability to pull that electron density. How about this NC bond? Again, look at the periodic table. Which atom is more electronegative? The nitrogen is. So it pulls electrons a little bit tighter. And again, this results in the polar covalent bond. And how about an SF bond? Fluorine's the most electronegative, so it's definitely pulling those electrons a bit harder than the sulfur. Okay, so these are polar covalent bonds. And so, since we have more electron density on one end, yes, as we've drawn, the partial negative is on one end, so it's pulling more electron density. These bonds have a dipole, okay? So we call this a dipole, and it's just really a direction of polarity. So the dipole of a bond is depicted using an arrow with a cross at one end, and the cross goes over the plus portion, the partially positive end, and then the arrow at the partially negative end. So for that carbon-oxygen bond that I just drew, right, it was partially positive over here and partially negative over here. So we would draw the bond dipole arrow like this. Okay, again, the cross is over the positive, and then it's pointing to where the electrons are more centralized or located. Okay, how about that NC bond? Again, here was the partial negative, and here was the partial positive part. So our arrow this time is going to be pointing towards the nitrogen. Again, the cross goes over the positive. And for that SF bond, right, again, fluorine's the most electronegative, so we draw our dipole arrow towards the fluorine. Okay, and so just as individual bonds are often polar, remember we mentioned that the majority of covalent bonds in all of chemistry are polar, okay? Entire molecules can also be polar. And so the entire molecules, though, their polarity depends on the vector sum, as in if we have the individual bond dipoles in a molecule, if they add up, they reinforce one another, then we're going to have a polar molecule. Okay, so it's the vector sum of those individual bond dipoles. Okay, so entire molecules are polar because of the net or vector sum of the individual bond dipoles and lone pairs, lone pair contributions. Lone pairs contribute a lot to overall polarity contributions. Okay, so we're going to look at the individual bond dipoles and kind of see if there is a net dipole in the molecule. These are really clearly seen in an electrostatic potential map. Okay, this first example here, this is just carbon tetrachloride, CCl4. You can picture the Lewis structure, right? It's got carbon in the middle with the chlorines on the outside, right? So it's got 4 charge clouds on the carbon, 4 charge clouds, which means it is what shape? Tetrahedral shape. So it looks like this. Right, and that carbon in the middle has a sp3 hybridization, right? Okay. And so if we look at the individual bond dipoles here, right, chlorine is more electronegative than carbon, so the electron density for each bond is going to be pulled towards the chlorines. And you can see it's definitely very symmetrical. Okay, again, just imagine this in 3D, it's being spread out, and all of those bond dipoles are being pulled, the electron density is being pulled in equal and opposite directions, right, because it's all symmetrical. So we would say then that this guy is symmetrical. I'll use black. So the bond dipoles are symmetrical. And so the dipoles cancel. So there's no net overall dipole. There's no net overall dipole. Nothing's reinforcing each other. And you can see that here in the electrostatic potential map. You can see there's no collection of electron density in either part of the molecule. It's pretty much just equally distributed. And so that's why this molecule is definitely non-polar. Okay? So conversely, here is chloroform, CH3Cl. Sorry, chloromethane. Again, it's the same shape, okay? We've got the tetrahedral carbon in the middle with the hydrogens and the chlorine around it. Again, it's an sp3 hybridized carbon because it's got 4 charge clouds, and so it's tetrahedral shape. Okay, and so now if we look at the individual bond dipoles, we don't usually draw the CH bond dipoles, and that's because they're just too small. Okay, so CH dipole, too small. It's pretty much negligible, so we rarely draw it. Negligible. But the CCl bond dipole, it's got lone pairs up there, it's definitely pulling electron density towards the chlorine. So then you can see we don't have bond dipoles canceling out. We just have this overall big old, not overall, but just in this bond we have electrons being pulled towards the chlorine. So then overall for the whole molecule, right, nothing is canceling, so we do have an overall dipole. Okay, so here's the net. And we can see that in its electron potential map. Okay, we have electron density surrounding that chlorine atom. And so again, the entire molecule, if you look at the entire molecule, we have red up here, blue down here, so there's an overall polarity, there's an overall net dipole towards that chlorine. Okay, so this guy is definitely polar. Okay, down here, this is just ammonia. And so we're including this one. Remember the shape of ammonia? Again, ammonia has 4 charge clouds on the nitrogen because it's got that lone pair. So it's tetrahedral shaped, okay? Generally, if we wanted to be specific, it's that trigonal pyramidal. And the lone pairs on nitrogen have a lot of pull. They pull a lot of electron density, okay? So the lone pairs pull a lot of electron density. Okay, so if we look at the individual bond dipoles, nitrogen is more polar than hydrogen, so we have these little dipoles pulling towards nitrogen, and then we have this big one with the lone pairs. Okay, they pull a lot of electron density because, I mean, after all, they are electrons. So then our net overall dipole, you can see that these guys are kind of reinforcing one another, going towards nitrogen, and then we have this bigger one with the going towards the lone pair. So this definitely has an overall net dipole, and we can see that again in the electrostatic potential map. Okay, going right up towards the top of those lone pairs. It's the net dipole. Again, those dipoles of the individual bonds are reinforcing one another to give an unsymmetrical electron distribution. We have more electron distribution at the top of the entire molecule, and so we have an overall polarity. Okay, so we are definitely polar. Okay, and right here is water. Remember the shape of water? It also has 4 charge clouds on the oxygen, right, because it's got 2 lone pairs, sp3 hybridized. Okay, if we look at the individual bond dipoles, again, we're being reinforced here because they're both pulling towards the oxygen, and then we have dipoles with the lone pairs. Those are being pulled. So if we were to draw the net dipole, kind of be going across like this, the net. And we can definitely kind of see that here in the potential map. Net dipole. Okay, so again, we are reinforcing, the individual bond dipoles are reinforcing, so we are again polar. We can't actually measure the polarity of a molecule. We can measure it, okay? It's called the dipole moment of the molecule, okay? And it's given in dBs, okay? So it's the abbreviated, or the short form is mu for the dipole moment, and it's measured in dBs. And so the larger the mu, the more polar the compound. Okay, so it's actually a measure of the strength of the dipole moment. The strength of this arrow is mu, okay? And so, can we guess what the mu would be for carbon tetrachloride? Do we think that it has a mu? Does it have a dipole moment? No. So mu is 0.0 Debye. Yeah. Okay. Here we go, chloromethane though. We do have an overall dipole, so it is polar. Its mu is actually 1.90 Debye. Okay, we can see that the electrons are being pulled, so it definitely has an overall dipole. Okay, ammonia has a mu of 1.47 Debye. Again, it's definitely polar. The electron density being pulled towards that lone pair. And same with water, right? Water has a mu of 1.85 Debye. Okay, so it's a little bit more than nitrogen because we've got two lone pairs. Okay, so we can actually measure the strength of the polarity, or the magnitude of the polarity of the molecule, and it's given in Debye, and it's called its dipole moment for the molecule. Okay, so in order to determine the overall polarity, there are multiple steps involved. Okay, nice and logical. First, you got to figure out the Lewis structure. Okay, you get the molecular formula, you draw the Lewis structure, we have an idea of the general shape, but then from the Lewis structure, right, we can figure out the charge clouds and really predict the three-dimensional shape. From there, we can draw the individual bond dipoles on the compound and then look at those bond dipoles. Okay, if they are symmetrical, then they're going to cancel out and result in a nonpolar molecule. Conversely though, if the dipoles are unsymmetrical, we have some reinforcement of those dipoles. Okay, they don't all cancel out, then they result in a net dipole, which means we have a polar molecule. So we have some good examples here with the different chlorines adding onto carbon. Okay, if we look at the individual bond dipoles here, we can see we have a distinct one between the carbon and the chlorine. I don't have any of my lone pairs, I'm sorry, on those chlorines. But we can see that the electron density is being pulled towards the chlorine, and so this definitely has an overall net dipole this direction, and a 1.9 Debye is what mu. We just went over this molecule before. Okay, here as we increase our number of chlorines on carbon, okay, if we draw our individual bond dipoles, we can see that we kind of get some canceling here, right? It's being pulled this way and this way. So there's some cancel of dipole. Some canceling of the dipole. And so we still have an overall dipole, okay, but the mu here is less, 1.59 Debye. Okay, that's because of that canceling out of the polarity. And here we're going to get even more canceling, okay, but we still do have an overall dipole, right, because we still have an H over here. Again, it's not going to be symmetrical, so I would say it kind of goes through the molecule like this, the net. And here the mu is still less, 1.0 Debye. Again, that's because more electron density is being pulled in almost equal directions. Okay, we're getting some canceling, but it is still unsymmetrical because we only have a CH bond here. And so here, though, we just saw this. If we throw in all of the bond dipoles now, we can see that they are being pulled. They are symmetrical, equal opposite directions, and so there's no net dipole. No net. Oh, why can't I write? No net dipole. And we saw that before, 0.0 for the mu. Okay, so just look at those vectors of the individual bonds, okay? Again, if they're symmetrical, okay, it's definitely all going to cancel out. But as long as we have some unsymmetrical aspect to the structure, then we are going to have an overall dipole, okay? So polarity has a significant effect on melting points and boiling points and other physical characteristics. So that's why we spend so much time on it, polarity. And it really has an effect on these intermolecular forces, okay? Intermolecular forces. So have you ever thought about why different compounds have different melting points or why they have different boiling points? Well, in order to boil or in order to melt, we have to overcome the forces that are holding the molecules in their current state, okay? So you can see here, this is a nice depiction of a solid. You can see that everything is ordered and packed very tightly, okay? And so they're stuck a lot. Stuck closest, okay? Here's a liquid. You can see there is less order in the molecules. They have a little bit more freedom, okay? So they had to get enough energy to kind of break away from their solid state. And then here's the gas. This is when things boil, right? And this is when they have the greatest motion because they're in the gas phase, okay? And so we can obviously see that they're sticking the least. Stick the least here. Okay, here they're all stuck together nice and tightly. In the liquid, they have a little bit more freedom, so they had to overcome the stickiness of the solid, and then to actually boil and have all this freedom, they again have to overcome the forces holding them in the liquid state. Okay, so that's what it says here. Compound samples have to have enough energy or enough heat to overcome the intermolecular forces. There's something holding them together in this ordered state as well as in the liquid. So we have to overcome each of those in order to get change phases. Okay, so these intermolecular forces are actually attractive forces. Are attractive. Again, it's the stickiness. Okay, they're attractive interactions. Importantly, they're between molecules. Between molecules. Okay, and they result in what I like to call a stickiness between compounds. So again, there's something holding them all ordered like this in the solid phase, and those are intermolecular forces. Same with the liquid. Something holding them together, they're sticking together, and those are intermolecular forces. And again, these are importantly between molecules, okay? But they are just interactions, okay? Forces are just interactions, okay? They're not formal bonds, okay? Not actual covalent bonds. You guys get mixed up with these things, okay? They're not actually forming a bond between each molecule. There's just a force between them, as in an interaction between them. An interaction, okay? So they're not actual bonds. We're not breaking any bonds when we boil. We're not breaking any bonds when we go into a liquid phase, okay? We're just overcoming the intermolecular forces between all of the molecules. Okay, and the strength of these forces rely heavily on polarity, okay? So these all depend on polarity of the whole molecule. So we spent so much time of it. And this, of course, is a result of shape. So you need to understand and be able to predict shape before you can predict polarity, to be able to predict the intermolecular forces between the molecules. Okay? In addition to melting and boiling, intermolecular forces also affect solubilities and are responsible for the shapes in biomolecules. So these are super, super important. Okay, there are three main types of intermolecular forces. Okay, the forces that kind of hold the molecules in their each state. Okay, there are three of them. First up is dipole-dipole. Dipole-dipole interactions. Second, we're going to talk about London dispersion forces. Dispersion forces. And finally, the strongest one is hydrogen bonding. Okay, so we'll talk about all these three, and they either reinforce one another or they are all interacting in a molecule to kind of, again, interact between molecules and kind of hold them together in like a stickiness. And so we have to overcome that to change phase each time.